Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 9, Determining the Equation of a Line Fit to Data. Okay, so classwork number example 1 says crocodiles and alligators. Scientists are interested in finding out how different species adapt to finding food sources. One group studied crocodiles to find out how their bite force was related to body mass and diet. The table below displays the information they collected on body mass in pounds and bite size force in pounds. So they're calling all of these crocodilian biting. Crocodilian. And that is just a bunch of different species. Dwarf crocodiles, alligators, caimans, and Nile crocodiles, Indian gharial crocodile, and American crocodile, and American alligator. So I have brought in pictures so you can see all of these. Okay, so there they are in order. So here's a dwarf crocodile. Here's a crocodile. Here's an alligator. Here's a caiman. This here is an Indian gharial crocodile. This is, no, that's the Indian right here. The Indian, no, that's the, let's see, I'm not sure. I lost track. But anyhow, these are all different types of gators. And finishing off with the American alligator. I think that's this one here. But anyway, you get the idea. They're very similar, except this guy here, he's got a really narrow snout. And so anyway, they're determining, and this is a dwarf, so this guy's a little guy compared to the rest. So they're taking bite force and how much they eat into consideration in this activity. So let's get rid of those pictures now. Okay. Okay, so this data that's in this table came from this link. The note says body mass and bite force have been converted to pounds from kilograms and newtons, respectively. So everything is in pounds. So the dwarf crocodile weighs 35 pounds. It's got a bite force of 450 pounds. And then if you go all the way down to alligator C, American alligator, alligator C is 365 pounds with 1,450 pounds of bite force. Okay, so anyhow, there's a table. So as you learned in previous lessons, it's a good idea to begin by looking at what a scatter plot tells you about the data. The scatter plot below displays the data of the body mass and bite force for the crocodiles in the study. So if I go back here, these are all data values that are being substituted or plugged into or entered into this chart. They're being plotted or graphed. So body mass is my x-axis and bite force is y. They're both in pounds. So for example, the dwarf crocodile's body mass is 35 pounds and has a 450 pound bite force. So 450 pound bite force, that would be this one right here. This would be the dwarf crocodile. Light, but got a pretty good bite. Okay, so anyhow, number 1 says, describe the relationship between body mass and bite force for the crocodile shown in the scatter plot. Okay, so when you're answering relationships, when you see describe relationships, you want to say, as X does something, comma, Y is doing something. And that's how we always say that. So in this situation, X is here and Y is here. So I would say as, well, what is X? X is body mass. As body mass increases, okay, as we go to the right, in other words, as the weight increases, what happens to the bite force? Does it get greater or less? Well, as we're going to the right, this is going up. So I would say bite force increases. Okay, so you always say as X, then Y does this. Okay, number 2, draw a line to represent the trend in the data. Comment on what you considered in drawing your line. All right, so I'm going to get my ruler. And if I rotate that so it's kind of, so if I'm going to draw a couple of lines. I'm going to erase the ones that I don't want to use. Okay, so I could draw a line there. And if I move this off now and look at it, we're trying to find where the data, let me get rid of this red dot here. All this data, the distances are fairly close to the line that we draw. And actually that's not really a bad representation of our best fit line. I might move it down just a little bit like that, because these are quite a bit lower and could pull it down. Maybe something like that. Okay, so what do you take into consideration when you're considering drawing a line? We've talked about this in prior lessons. You could connect the first point to the last point, but that may not always be the best way. I just like to draw it so that it looks like there's an even amount of distance added up, so it's like an average line. So if this is a distance of 320, then we add all those distances up, and they should equal the sum of all the distances of the dots below. And if they're right on the line, then you don't count them, and that kind of thing. Okay, so there's my best fit line for 2. Number 3 says, based on your line, predict the bite force of a crocodile that weighs 220 pounds. So what they're asking us to do is, now that we have this line, make our vertical line with our ruler, and I want a 200-pound body mass, so I'm going to put this at 200 pounds, and I'm going to draw that line right there. So at 200 pounds, we hit our line of best fit right there, and if I rotate this down like so, then I can find where that is on the y-axis, and it's just under 800 pounds. So I would say predict a bite force that would 220 pounds, not 200 pounds. So where's 220? Well, here's 300, 250, 220 might be a little bit more to the right here. This is 200, so 220, 1/5 of the way, might be right about here. So in other words, then we're moving this point to here, and now it's a little bit heavier. So if I move this up here, I'm a little over 800, let's say 820 pounds or something like that. Okay, so when the crocodile weighs 220 pounds, bite force is approximately 825 pounds, I'll say. How does this prediction compare to the actual bite force of the 220-pound crocodile in the data set? So now I'm going to look for 220 for the weight of the crocodile, and 220 is right here, and its bite force was 1,000 pounds. Okay, so when I look at that, a 220-pound crocodile should have been 1,000 pounds, which is right here. So I'm low. So how does it compare? Our prediction is low. Okay, number 4 says several students decided to draw lines that represent the trend in the data. Consider the lines drawn by Saul, Patty, Marissa, and Taylor, which are shown below. Here's Saul, Patty, Marissa, and Taylor. For each student, indicate whether or not you think the line would be a good line to use to make predictions. Explain your thinking. Okay, so I'm not going to write these, I'm just going to explain it. It's a lot of writing and it's hard to write with this pen. For each student, indicate whether or not you think the line would be a good line to use to make predictions. Explain your thinking. Well, if I look at this here, every single data point until right here is the line is underestimating the bite force. Every point beyond that is overestimating the bite force. So I don't think Saul's line is a good line to fit. Okay. Now let's move down to Marissa. Notice that Marissa's, there's a point here that's close to on but just above these 4, but all of these data points are below. So this is a way overestimate. So if something weighed 225 pounds like this gator, or whatever one that is, Marissa's line is saying that it would have a bite force over 1,000 pounds when it really has a bite force of 400 pounds. So this is way off. Okay. This line here, let's look at Patty's first. Patty's. So Patty's has a whole bunch of points above. There's a couple on, and then there's these 4 that are below. This one looks like a pretty good line of fit because the ones that are below are quite a ways below. So these kind of line up pretty good. Okay, so I like Patty's line so far. Taylor's line, now look at all these points here are all above, which means that this line is underestimating all of those bite forces. And there are a few below, but they're closer. So I would say that Taylor's is an underestimate, and Marissa's line's an overestimate, and Saul's line is off both ways. One way, when you're talking about a light alligator, you're saying that it's got a weaker bite force than it does, and then when they get bigger, it's got a stronger bite force than they actually do. So that's off at both ends. So I think Patty's line is the best one. Okay, number 5. What is the equation of your line? Show the steps you use to determine your line. Based on your equation, what is your prediction of the bite force of a crocodile weighing 200 pounds? Okay, so if I'm going to use a prediction of my line, I'm going to go back to that line. And if I look at, I don't know, let's take a look at Patty since we agreed on that. I'm going to use this point right here, which was 325. The X value is 325 pounds, and the Y is 1,200. There's one point. Okay, and then I'm going to look for another point maybe down here, and that looks like it's about 40 pounds and has a 75 pound bite force. So if I use those 2 points, I'm going to find a slope. So I have 325 comma 1,200. There's one point, that's point 1. And point 2 has 40 comma 275. 40 comma 275. The second point I chose. Okay, so keep in mind that we want to know what a slope is. So slope, or the rate of change, is y2 minus y1 divided by x2 minus x1. Y2 is 275 minus 1,200 divided by x1, which is 40, x2 minus x1, which is 325. Okay, so 1,200, 275 is a difference of 925, and it's negative. And 40 minus 325 is 285, I believe, negative. A negative divided by a negative is positive. And I will use my calculator to do this calculation. So 925 divided by 285 is 3.25 roughly, which is approximately 3 1/4. And I'm going to make that an improper fraction, which is 13 over 4. That's an approximation of my slope. So I say y equals 13 over 4x plus, and my y-intercept is right here, and that's about 110, let's just say. So there's an equation of a line of fit. And it says, based on your equation, what is your prediction of the bite force of a crocodile weighing 200 pounds? So I'd say y equals 13 over 4 times that 200 plus 110. Well, this is going to turn that into 50. So y equals 50 times 13. 650 plus 110. So my bite force is 760 pounds. 760 pounds for a 200-pound crocodilian. So if I go back, a 200-pound crocodilian, and I came up with what? 760-pound bite force. So we're looking for 200, 760. Go back to the beginning. Find a 200-pound crocodilian. And there aren't any 200-pounders, but the closest one is 220. And it was a 1,000-pound bite force. And my approximation was 760. So my estimate is a little low, but it's fairly close. Okay, number 6. It says Patty drew vertical line segments from 2 points to the line in her scatter plot. The first point she selected was for the dwarf crocodile, and it's labeled right here. The second point she selected was for an Indian gharial crocodile, and that's right here. A. Would Patty's line have resulted in a predicted bite force that was closer to the actual bite force of the dwarf crocodile or the Indian gharial crocodile? Well, what they're asking is which point is closer to her line of best fit. And this has a distance of, we're going from 400 to actually over 400 difference. And this is about less than 500 going down to over 200. So obviously the dwarf crocodile is closer. So, which was closer? The dwarf. So it says, what aspect of the scatter plot supports your answer? Well, the distance from your actual line of best fit. So the closer your point is to the line of best fit, the better the closer that value is, the better the estimate. Closer to the actual bite force. The further you are from the actual. So B says, would it be preferable to describe the trend in the scatter plot using a line that makes the differences in the actual and predicted values large or small? Explain your answers. Okay, well, you'd want a small difference because that would put you closer to the actual. WOULD. Okay, smaller difference is better because that would put you closer to the actual bite force. Exercise 7, used cars. Okay, exercise 7 says used cars. Suppose the plot below shows the age in years. Age in years, so as the car is getting older, price of the car is doing what? Use the compact cars that were advertised in the local newspaper. A, based on the scatter plot above, describe the relationship between the age and price of used cars. Remember what I said. As X does what, comma, Y does this. So I would say as the age of the cars, or of cars, sorry about that, lost track of time, that was our bell. As the age of cars increases, they get older, the price or the value decreases. Oops, decreases. Okay, there we go. As the age of cars increases, the price decreases. B. Nora drew a line she thought was close to many of the points and found the equation of the line. She used the points 13, 60,000 or 6,000 and 7, 12,000 on her line to find the equation. Explain why those points made finding the equation easy. Well, if we go over to 13 and 6,000, that's a point that is right on the line. And when she went to 7 and went up to 12,000, that's this point right here. Why would those 2 points make finding the equation easy? Well, to find slope, we take the y, so this is x1, y1, and this is x2, y2. So what we're saying is 12,000 minus 6,000 over 7 minus 13. So when we do that, we get m equals 6,000 over negative 6. And therefore, a positive divided by a negative is negative, and 6,000 divided by 6 is 1,000. So why did that make it easy? Because the difference of the x's is 6, and the difference of the y's was 6,000, and that 6 goes into 6,000 evenly, and that's why it made it easy. Okay, and the points were on the corners of the grid, so they were on integer coordinates. So there was no approximations. C says to find the equation of Noah's line to predicting the price of a used car given its age. Summarize the trend described by this equation. So I'm going to write y equals, and we already have the slope. We found that on that last problem. Okay, so it's y equals negative 1,000x. And then all I have to do is come up here and find where it would cross. But the problem is, if I drew a line through here, we're off the grid up here. So I'm just going to put a B here. Now I'm going to substitute in an x and a y that we were given. So I'm going to put those here. So this is x and this is y. And how about we use a point she used for her slope? Let's use 13, 6,000. So when x is 13, y is 6,000. So when I do that, my y is 6,000. My slope is 1,000. My x is 13. And all I need to do now is find b. So when I simplify, negative 1,000 times 13 is negative 13,000. If I add 13,000 to both sides, I find b. So these cancel because they're opposites, leaving b by itself. 0, 0, 0, 6 plus 3 is 9, and 1. So b is 19,000. So now my equation is y equals negative 1,000 x plus 19,000. There, y equals 1,000x plus 19,000. Okay, so I just said y equals 1,000, but it is negative. Make sure you're clear on that, because as we're going to the right, as the age of the car increases, the price decreases, so it's a negative rate of change. All right, D, based on the line, for which car in the data set would be predicted value of the farthest from the actual value, and how can you tell? So I'm going to go back here. Let me get rid of this. Okay, let me get my ruler. And I am going to actually draw that line, and I'm going to use the points that she used. Actually, it's already done somewhere. Where is it? Right here. Which one is furthest? So I still want my ruler. So I'm going to use that. So what I'm going to point out to you is, if I rotate my ruler like so, and I'm looking for the one that is the furthest away. And if I look at this dot right here, that dot is that distance away from that line, and there's no other line further than this point right here, which is the 10-year-old car for $4,000. Okay, and it says, how can you tell? Well, I just showed you with the rule. E, what does the equation predict for the cost of a 10-year-old car? How close was the prediction using the line to the actual cost of the 10-year-old car in the data set? Well, actual we just found when I just did that last problem. 10-year-old car was $4,000. That's actual. But if I go back and look at predicted 10-year-old car, what we're talking about now is this point here. The point on the line is our prediction. If I rotate my straight edge here and put it here and come over here, I see that it is 9,000. So actual was 10,000 or $4,000 for a 10-year-old car, and the predicted for a 10-year-old car was actually $9,000. I don't want to use another comma. That separates our X and our Y. Okay. So given in the context of the data set, do you think the difference between the predicted price and the actual price is large or small? Well, it's more than double, so it's very large. That is a huge difference. Okay. Predicted is more than double the actual. F, is $5,000 typical of the differences between predicted prices and actual price for the cars in this data set? Justify your answers. Okay, so what they're saying is, are these lines on average a distance of 5,000 away from the line? So if I look at this point here, 16,000's actual, a little more than 15,000's estimated, so it's less than 1,000 difference. So this is about 1,000, a little more, and these are really close. And then this one's the furthest away besides our real far one. So from here to here, we're going from like 3 to 5, like 2,000. So the largest value other than this one is 2,000, then they get closer and closer. So to answer this question, 5,000 typical of the difference? No, it's too large. The difference should be more like 1,000, I would say. Okay, that is the end of lesson 9. Read the lesson summary and go do your problem set.